So today, the standard way of representing integers inside a computer system is to use the two's complement representation. But let me talk about signed integers in general, and then I'm going to show you why people use today the two's complement representation. So when we think about signed integers, we think about negative numbers, of course, in addition to the positive numbers. So one way to represent them is to use the sign magnitude representation. Sign magnitude is very simple. We can dedicate one bit to be the sign bit. Now, there are only two possible signs. Either the number is positive or negative. That's it. So therefore, only one bit will be sufficient. So 0 means plus and 1 means minus. Okay, so we can use the sign magnitude representation to represent a signed integer. We can also use other representations, for example, the ones complement and the two's complement. So I need to talk about these three different representations. And the focus will be on the two's complement representation because this is the standard way of representing signed integers inside computers today. So the way that we deal with integers is that we can divide the range of values into two parts. The first part, the first half, if you would like, will be the positive numbers, which are greater than or equal to 0. So here 0, okay, is also included. So therefore, greater than or equal to 0, these will be the positive numbers. And we have the negative numbers, which are strictly less than 0, okay? So let us start first with the sign magnitude representation. So we have a number that consists of n bits, and one bit will be dedicated as the sign bit. So this sign bit is the most significant bit. It appears as the leftmost bit inside the number. And the remaining n-1 bits are used as the magnitude. So this is why it's called the sign magnitude representation. That's the meaning of sign magnitude. So this most significant bit here can be 0 or 1. Okay, so it can be either 0 or 1. So 0 means that the number is positive, and 1, it means that it is negative. That's as simple as that. So for example, if I would like to represent plus 45, okay, using the sign magnitude representation, so the most significant bit here is 0, that's plus. And the remaining 7 bits here will represent the number 45. So let me just write 45 carefully here. If you would like to represent negative 45, you use 1. But use exactly the same bits here to represent 45. So that's minus 45. Okay. So this will be the 8-bit representation. We use 1 bit for the sign and 7 bits for the magnitude. Now, in general, if you have n bits, you have 1 bit for the sign and n-1 will be the number of bits for the magnitude. Then you can say what's the largest magnitude that you can represent using n-1 bits. It will be 2 to the power n-1 minus 1. The smallest magnitude will be 0, and the largest will be 2 to the power n-1 minus 1, because we are using n-1 bits. Okay, so this is the largest magnitude, and this will tell you how large you can represent a number using the sign magnitude representation. Now, sign magnitude has certain properties. First, the range is symmetric. You can go from negative 2 to the power n-1 minus 1. That will be the smallest negative number. And the largest positive will be plus the same magnitude, 2 to the power n-1 minus 1. And for example, if n is equal to 8 bits, if we are using here 8-bit register, so a register is used today inside the CPU to store a number. It's a memory element. So we can use n-bit register, okay, to store an n-bit number. So if you use, for example, 8-bit register, n will be equal to 8 bits, then the range will be from negative 127 to plus 127. This is the range of values that you can represent using the sign magnitude representation. Just 1 second. So now we have two representations for 0. The problem with sign magnitude is that we have two representations for 0. We can have +0 and we can have -0 because the sign bit is separate. Now we have two possible representations for 0. So +0 and -0 are both possible under sign magnitude, which is not good. And we don't really would like to have -0. Why do we need two representations for 0? One representation for 0 is sufficient. Another problem which is related to sign magnitude is that we need two circuits, okay, to do addition and subtraction, which is not really good. So sign magnitude is going to complicate the implementation of this circuit in the hardware. So to do addition and subtraction, it's more complex. It becomes complex when you would like to use the sign magnitude representation, because we have to look at the sign bit. We should examine the sign bit to determine whether we are adding or subtracting. And this is going to increase the cost of the circuit that does addition and subtraction. Now, this slide explains why it becomes more difficult to design a circuit, okay, using the sign magnitude representation. If we have two numbers A and B in the sign magnitude representation, of course, A can be positive, B can be positive, A can be negative, and B can be negative. So A and B each one has a sign. So A can be positive or negative, B can be positive or negative. And then we have the operation. The operation can be addition, plus, or minus means subtraction. Okay? So either we are adding or we are subtracting. So in total, we have 8 cases to take into account. So now we can say, okay, how do I add and how do I subtract when the numbers are represented in the sign magnitude representation? Well, we have to take them case by case. Okay, that's what we have to do. If I'm adding two numbers which are positive, let us take the first case here. If I'm adding two numbers which are both, we can check their sign bits. And if the sign bit of A is positive and the sign bit of B is also positive, so we're adding two positive integers, the sum must be positive. So we can add the magnitudes of A and B, and we can indicate that the sign is a plus. We know that in advance because the sign bits of A and B are both positive. Very simple. So that will be the result if you are adding two positive integers. Now, similarly, if you are adding two negative integers, so suppose that A is negative and B is negative, so both of them are negative. This will be here case number 4. Now, because you are adding two numbers of the same sign, you can add the magnitudes and you can show that the sign is negative. So you can design a circuit that does this. So again, we are going to add the magnitudes, but you specify that the sign is negative. Now, what is the problem? The problem is that if you are adding two numbers that have different signs, these two cases here. So if you are adding a positive A to a negative B, or you are adding a negative A to a positive B, now this is not addition, this is subtraction. Why? Because we are adding numbers that have different signs. So how do we calculate the result? Well, we have two cases here. Either we have A is greater than or equal to B, or we have A is less than B. So the magnitude of A is greater than or equal to the magnitude of B, or the magnitude of A is less than the magnitude of B. So if A is greater than or equal to B, we calculate A minus B. And then we specify the sign to be either plus or minus. So we have to calculate the magnitude and we have to determine the sign. However, if the magnitude of A is less than the magnitude of B, that will be another case. We have to calculate B minus A. And then we have to show the sign, either negative or positive. So you see that we need a comparator to compare the magnitudes of A and B to determine whether the sign is positive or negative, and to do the subtraction. So you see that this is really complex. So to design such a circuit that does the addition and subtraction of sign magnitude integers is not really simple. The same thing can be said for these 4 cases here, okay, when we are subtracting. So when we are subtracting 2 positive integers, then what we have to do is that we have to subtract, and either we get plus A minus B or we get negative B minus A. Notice that here this is plus A minus B. So I'm subtracting here minus B. I can convert it into addition, and we can know that the result is plus. Or we have negative A minus plus B. So we can add the magnitude of A plus B, and we can indicate that this sign is negative. So we have to take into account all of these 8 cases to determine, okay, the correct sign and the correct magnitude of the result. Okay, so that's really the major problem with the sign magnitude representation. Ali?
So, Doctor, we should put the positive number first.
Well, the numbers actually are provided into an arithmetic unit inside the CPU, so they can appear in any order. So you might actually have plus A, minus A, plus B, minus B. It could be addition, it could be subtraction. In all cases, we should really determine the correct sign and the correct magnitude.
Inside the bracket, I cannot say minus B plus A. I should take the minus out.
Well, what you have to do is that, okay, you are talking about which case? Which case?
The second case.
The second case here, right?
Yes, when B is bigger than A.
Well, yes, so that will be here.
Yes.
So what you have to do is that you have to subtract the magnitudes. Okay, to get the magnitude cannot be negative. So this is why we calculate B minus A, and we indicate that the sign is negative.
Ah, okay, now I understand. Thank you.
Yeah. So this is why we have to subtract their magnitudes. So we subtract B minus A. So this is all based on whether the magnitude of A is greater than or equal to B, or it is less than B. So we have to actually do the subtraction to determine the magnitude of the result and the sign of the result. Now, this is complex. It's not really simple. And for this reason, computers today, they don't use the sign magnitude representation. There is a much better way to represent sign integers that I will talk about it in this lecture. So how do computers represent sign integers? If sign magnitude is not used, what do they use? Well, the standard way to represent sign integers today is the 2's complement representation. But before I talk about the 2's complement, let me talk briefly about the 1's complement representation. So what's the meaning of 1's complement? The 1's complement is obtained, if you would like to take the 1's complement of A, you obtain it by inverting all the bits of A. So the meaning of 1's complement is that it's inverting each bit of A. That's the meaning of 1's complement. Yani, for example, if this is A, and you would like in binary, and you would like to obtain its 1's complement, the 1 becomes a 0 and the 0 becomes 1. So this is basically the 1's complement of A. So the 1's complement of A is nothing but A prime. That's it. You take each bit and you complement it. So the 1 becomes 0 and the 0 becomes 1. So that's just A prime or not A. So you complement it bit by bit, bitwise. Okay. So that's the definition of the 1's complement. You invert. Okay. Very simple. Like, what is the implication of this? If you take A and you add to it A plus the 1's complement of A, when you add the 0 plus 1, you get 1. If you add 1 plus 0, you also get a 1. So therefore, when you add, you get all 1's. And if this is A and this is the 1's complement, and you add these two numbers, you will get all the bits to be all ones. Correct? That's basically the implication of adding A plus the ones complement of A. So all the bits are all ones. And if you would like to look at its decimal value, it will be 2 to the power n minus 1. Okay? So if you look at all the ones here as an unsigned integer, it will be 2 to the power n minus 1. Right. So this is one thing about the ones complement representation. Another thing is that what's the range of values that you can represent? It's the same as in the case of the sign magnitude. You can go from negative 2 to the power n minus 1 minus 1 to plus 2 to the power n minus 1 minus 1. So for example, if n is equal to 8 bits, you get exactly the same range. Now, again, we have the same problem as in the case of the sign magnitude. You get two representations for 0. You have plus 0 and you have minus 0, which is not good. So we have two zeros. And if you look at the ones complement of 0, you get all ones. So that's negative 0. Negative 0 is all ones. That's in the ones complement representation. And this is not really good. So we have two zeros, and for this reason, people don't like to use the ones complement representation. It's not really used today in circuits, okay, or they are not really used to represent signed integers, right? So what do people use? They use the 2's complement representation. So the 2's complement representation is the standard way to represent signed integers inside computers. What's the definition of 2's complement? If you have any number A, okay, so given any number A, if you would like to obtain the 2's complement of A, you take the 1's complement of A, and then you add plus 1. That's it. So you add it, of course, in binary. You take the 1's complement of A, so that actually is A prime, and then you add to it plus 1. If you do this, then you get the 2's complement of A. So this is the definition of the 2's complement of A. I'm going to show you an example in the next slide. I have an example here. And if this is A, okay, then this will be A prime. That will be the 1's complement. And then add plus 1, that will be the 2's complement of A. So this number here is the 2's complement. Okay, that's the 2's complement of A. It's the 1's complement plus 1. So the 1's complement is useful for calculating the 2's complement. That's why actually people talk about the 1's complement, because they use it to calculate the 2's complement. It's the 1's complement plus 1. That's the 2's complement. Now we have seen in the previous slide that if you take A plus A prime, yani the 1's complement of A, you get 2 to the power n minus 1. So basically you get all the n bits are all ones. Now, if you say A plus the 2's complement of A, the 2's complement is A prime plus 1. That's the 2's complement. What do you get? You get 2 to the power n. It's 2 to the power n minus 1 plus 1. You get 2 to the power n. So therefore, A plus the 2's complement of A is equal to 2 to the power n. This is very important. Remember this property mathematically. A plus the 2's complement of A is 2 to the power n. I'll come back to this point in a later slide. This is important. Right. So that's basically, okay, the meaning of the 2's complement. I have here some examples about how to compute the 2's complement. So let us take a look at this example. This is my number A. So this is A, which is shown in binary. Now, the decimal value here is plus 36. Again, we use the most significant bit as the sign. So that's indication of plus. And the when you look here at the decimal value, you get 36. Yani this bit here is 4. And this bit here is 32. So 32 plus 4 is equal to 36. That must be actually plus 36. We are not going to use here sign magnitude. We are using the 2's complement representation. If I would like to obtain the 2's complement of A, we have to do it in 2 steps. So step number 1 is to obtain the 1's complement. So let us invert all the bits. So this will be A prime. So So let me write here A prime. So the 0 becomes a 1 and the 1 becomes a 0. That's it. So that's step number 1. Invert all the bits. And this is by definition the 1's complement. Step number 2 is add 1. So notice that we are saying here plus 1. And then add in binary. So 1 plus 1, we get a 0, there is a small carry. This carry plus 1, you get a 0 and another carry. The carry plus 0, you get a 1, and all the upper bits, okay, will be the same. So basically, this number here is the 2's complement of A, and this is by definition negative 36. So when you start with plus 36 and you take its 2's complement, then you will get the binary representation of negative 36. So the 2's complement of A is the negative. Okay, so that's how we are representing, okay, the negative number. Okay, so that's the binary representation of the negative 36. Any question about this? Fine. So all what you have to do is that start, okay, let us say with a number A and take the 1's complement and then add plus 1, you will get the 2's complement. Now notice that we can start also with A equal to negative 36. And if I would like to get the 2's complement of negative 36, I'm going to get the plus 36. So let us do it. Okay, so now if my number is negative 36, let us take the 2's complement of negative 36. So I'm going to invert all of these bits and then add plus 1. So you get a 0 and the carry. You get a 0 and the carry. Here you get a 1. And all of these bits will be identical. And this number is equal to what? Plus 36. So when you take the 2's complement of a negative number, it will give you the positive value. And when you take the 2's complement of the positive, you get the negative. So the 2's complement of the 2's complement of A is equal to A. Okay, that actually is very clear, very shown here. So let me just erase this ink. So if you start with negative 36 and you take its 2's complement, this will give you plus 36. Okay. So the 2's complement of the 2's complement of A is equal to A. So think about the 2's complement as the negative operator. So the 2's complement of A is negative A, and therefore when you take negative A should give you A. Okay, so basically you get back to A. Do you have any question about this? Is this clear? So this is how we compute the 2's complement. There is a quick way of computing the 2's complement. There is another way, okay, and a faster way. If you would like to do it by hand, rather than obtaining the 1's complement and then adding 1, let me show you a fast way to obtain the 2's complement. So let us take the number plus 36 again, and then look at the least significant one. So start from the right, skip the zeros until you encounter the least significant one. Now, when you would like to take the complement, the 2's complement, we keep the 0, and the 1, and then we complement all of the bits that appear to the left of the least significant one. So these bits here are complemented. Okay, but the 0 and the 1 are not changed. They are the same. So this will be negative 36. So we did not really take the 1's complement and added 1. That's another way of obtaining the 2's complement. Okay, it's just we start from the right and until we encounter, so we skip the zeros until we encounter this one, the least significant one, keep it 1 and complement all the bits that appear to the left of this one. Okay, and this is how we obtain the 2's complement. That's another way of doing it, and this is a faster way. It will be exactly the same answer as taking the 1's complement and adding 1. Questions? Everything is clear?
Yes.
طيب. Yes, Ahmed, you have a question?
No, I think it's clear.
طيب. So now you can see that the meaning of the 2's complement, okay, it's basically if you would like to obtain the negative of a number, we take its 2's complement. That's the way that we represent signed integers. This is what we call the 2's complement representation. Now, the 2's complement representation has certain properties, and we'll see that its properties, okay, makes it actually really good to represent signed integers. First of all, there is only 1 0. So we don't really have negative 0 and positive 0. There is only a 0. That's it. And all the bits are all zeros. So there is only one representation for 0, which is good. So we don't really have 2 zeros like in the case of the sign magnitude or the 1's complement. So 2's complement, there is only 1 0. Now, if you take the 2's complement of 0, you will get all zeros. Notice that there is no 1 in it. Okay, so all the bits are all zeros. So if you take the 2's complement of 0, you will get also 0. Okay, that's one thing. Another thing is that concerning the range, okay, if you have, for example, n is equal to 8 bits, the range will be from negative 128 to plus 127. So the range in general, if n is for n bits, you will say that the smallest, the minimum negative is negative 2 to the power n minus 1, and the maximum positive is plus 2 to the power n minus 1 minus 1. So you have, for n bits, you have 128 negative values, starting from negative 1, negative 2, all the way to negative 128. And the other half will start from 0 all the way to 127. Okay. The meaning of the 2's complement is the negative of a, as I mentioned. And then if you take a plus the 2's complement of a, it must be 0. I have an example about this. So let us take this number here, which is a, which is equal to plus 44. So I'm going to write it like this. Okay, so this is here 0, 0, 1. This is 0, 1, 1, 0, 0. Now we can verify that this number, of course, from this most significant bit here, which is 0, it indicates that this number is positive. And because it is positive, we can look at the weights. So this is 4 plus 8 plus 32. So this will give me 44. So that's the decimal value. If I would like to take to obtain the negative 44, I'm going to keep the 0 and the 1 until I encounter this least significant one. And then I'm going to complement all the bits that appear to the left of this one. So complement all of these bits. So this one becomes 0, this is 1, this is 0, this is 1, this is 1. So that's negative 44. Okay, maybe I cannot really show it clearly here. Okay. So that's negative 44, it's actually shown. Okay, so I'm just copying it. So now let us add them in binary. If I would like to add plus 44 plus negative 44, so 0 plus 0 equal to 0, this is 0. Now 1 plus 1, you get 0 and the carry. Now you have the carry, 1 plus 1 plus 0, you get a 0 and another carry. Again, you get here 1 plus 0 plus 1, you get a 0 and the carry. Again, 0 and the carry. 0 and the carry. And then finally, we have 0 and a final carry. So notice that the answer is 0. So when you look at the sum here as 8-bit sum, so when you add a plus the 2's complement of a, it's like a plus negative of a. You should really always get 0. And you get this final carry here. But this final carry is not part, it's actually shown here. This final carry is not really part of the sum. Okay, so we ignore it. So even though we got the carry is not itself part of the sum. The sum is only equal to 0. That's my sum. And the final carry is ignored. We just ignore it. Okay, in the case when you are dealing with 2's complement integers. So integers which are represented in the 2's complement representation. Yeah, that's so we ignore the carry. Now remember that from the previous slide, I talked that a plus the 2's complement of a should give you a 0 and the carry. The carry here is 2 to the power n. So this carry here is 2 to the power n. N is equal to 8. So this carry here is 2 to the power 8. It's ignored because we will always get, when you add a plus the 2's complement of a, you will get this carry, 2 to the power n. Okay? So the sum equal to 0. And this final carry is ignored. Okay, so these are properties of the 2's complement. Any questions about this? Am I moving too fast? Is this clear? By the way, this material is included in the next quiz number 4. Also, is going to be included in the midterm exam. So it's why this is why it's important to raise questions now. I mean, I don't see you raising questions as if you understand everything. And this is not really good. Yeah, you have to raise questions. طيب. Now let me summarize what I said. We have seen the 2's complement representation. Let me make a comparison between unsigned and signed integers. At the beginning of the semester, I talked about unsigned integers. We did not really deal with negative numbers. So both can be represented inside the computer. Yani for example, if you have programmed in a C language, there are many languages like C, C++, and other languages that distinguish between unsigned and signed integer. And for example, in the C language, you have the type int that will be signed, and there is also unsigned int. So they use the keyword unsigned. So when you use unsigned, it means that the number can never be negative. You start from 0 up to a certain maximum. That's the meaning of unsigned integer. Like if I would like to represent an unsigned 8-bit integer. So here I have my number consisting of 8 bits. Okay. So if we restrict n to be 8, then we can start here at 8 zeros, and we can go all the way here down to 8 ones. Okay. So we have 256 possible, 2 to the power 8 equal to 256. So the smallest unsigned value will be 0, and the largest will be 255. But this if the number is unsigned. However, if the number is signed, we treat the most significant bit here. So this most significant bit is treated as the signed bit. So half of them will be greater than or equal to 0. So these are the positive values. So we start at 0, and we go all the way to plus 127. So these are identical to the unsigned values. So these are the decimal values. But the second half, which is shown below this red line, these are the negative values. So if the number is signed in the 2's complement representation, then we can have the numbers we start here at negative 128. So rather than having here 128, it becomes negative 128. This will be negative 127, and this becomes negative 1. So this will be the signed value. Right? Who gives a meaning, okay, to the decimal value? How do we know if a number is unsigned or signed? Do you know?
The 0 bit, the bit in the left.
Well, you see, the bit in the left is important when you are dealing with signed values, but it's not really signed magnitude. Yes, of course, we know that if it is negative or positive, okay, based on the most significant bit, yes, but that's assuming that the number is signed. But if the number actually is unsigned, then it can never be negative. So in other words, if you look at this number here, okay, the last one, all ones, you can give to it two meanings. You can say that this number is 255, or you can say that this number is -1. Because if you take the 2's complement, you will get +1. So this number must be -1. Okay. So how do I know if this number is 255 or it is -1? Well, let me answer this question for you. Okay, so the hardware does not really give a meaning. Yani the hardware will just look at the bits as bits. So the bits have no meaning inside the hardware. It's the software that gives meaning to these bits. Yani for example, as I said, if you are programming in a high-level programming language, the programmer is giving a meaning to these bits. So the programmer can say that these bits here are either unsigned. For example, if you are using the unsigned keyword, and therefore this will be the number 255 because it can never be negative, because the programmer specified that this type is unsigned. Or if you are actually using the type signed or just integer, for example, then it will say that no, the decimal value is -1. So it's changing the meaning of these bits. It's giving a different decimal value, even though the bits are represented exactly the same way inside the hardware. So when you are storing 8 ones inside an 8-bit register inside the CPU, you can give two different meanings. You can say that this number is either 255 or this number is -1. Now, who is going to say that this is 255 or -1? It's not the hardware. It's the software, the programmer. So the programmer will give a different meaning. So the interpretation of the bits is done by the programmer. So the programmer will say that this is -1 because I'm assuming that now this type is signed, not unsigned. Okay. So therefore, we change the decimal value in the case of when we are dealing with signed values. So 128 becomes -128. 129 becomes -127. Is there a relationship between unsigned and signed? Yes, there is a relationship. We can say that the signed value is the unsigned value minus 2 to the power n. N here is the number of bits. Yani, for example, if n is equal to 8 bits, you say minus 2 to the power 8, which is 256. Yani, for example, when you say 255, let us take a look at the last row. So 255 minus 256 will give me the -1. So that's the relationship between the signed value and the unsigned value. So they are related. Right. Is there a direct way to obtain the signed decimal value of a number? Let us take a look at this number here. Well, if this number is signed in the 2's complement representation, well, the only difference between signed and unsigned is that the most significant bit will have a negative weight. So again, it is a weighted number. So we're using a weighted number system, except that we are assigning a negative weight to the most significant bit. So rather than using plus 128, we are using minus 128 if the number is represented in the 2's complement representation. This is not in the sign magnitude. This is 2's complement. So therefore, we say that this bit here is minus 128. This is 32. This is 16. And this is 4. If you add them up, you get -76. So this number here, which is in binary, this binary number, which is shown here, is the number -76. So its decimal value is -76 if we say that this number is signed in the 2's complement representation. So we can get directly from the binary representation, we can get the decimal value. If we say that this number is unsigned, so we change it from minus 128 to plus 128, we get a different decimal value. we get the unsigned decimal value. Okay? Questions about this? You are silent, very silent. Okay, I have 33 students in this and nobody talks. Okay, which is okay. طيب, let us move on. Okay, so now what we have seen is that we have seen 3 different ways to represent a signed integer. Either we have signed magnitude, or we have 1's complement, or we have 2's complement. So these are 3 ways to represent a signed integer. Or we can say that the number actually is unsigned. So again, I'm going to show you a table that will summarize the differences. So if the number is represented in 8 bits, we can start here at 8 zeros, and we can go all the way here to 8 ones. So we have 256 possible combinations in binary. So if the number was unsigned, we start at 0, and we can go all the way here to 255, because it can never be negative. Right, if it is signed magnitude, we can start at +0, and we can go to +127 based on the most significant bit. So this most significant bit indicates a plus. And in the case of negative numbers, we start here at -0, and we can go to -127. So the problem here is that we have +0, -0, and this is not good in the case of the signed magnitude representation. In the case of the 1's complement, we start at +0 and we go to +127, exactly the same decimal value for unsigned and for signed magnitude. So the positive values are exactly identical, but the negative values are different. So the first one will be -127. It's not no longer -0 in the case of the 1's complement, because if you take the 1's complement, you will get actually 0 and all ones. So therefore, it will be the 1's complement will be +127. So this must be -127. So you can see there's a reflection here. You can see there's a reflection, right? So this must be -126, and then we have -0. So all ones in the 1's complement will be -0. Again, this is not good because we have +0 and -0. And for this reason, people don't use the 1's complement to represent signed integers. So the standard way is to use the 2's complement. This is the standard way to represent signed integers. So again, from 0 to 127, they are identical. There's only one representation for 0. All the bits must be zeros. And we end here at +127. And notice that 1 followed by all zeros, that will be -128. So we have a new value here, which is -128. Because this is the weight of the most significant bit, which is -128 plus zeros will be -128. And all ones, this last entry here, will be -1. So if you would like to calculate the weights, it's -128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 will give me -1. So that's my representation for -1. So all the bits will be ones if you are using the 2's complement representation to represent the decimal value -1, then all the bits must be all ones. So that's -1. Okay. So there is a big difference between signed magnitude, 1's complement, and 2's complement representation. And as I said, our focus will be on the 2's complement representation. So you should really know the differences between them, but this is the standard way to represent signed integers by computers. So today, almost all computers use the 2's complement representation when they are dealing with signed integers. So we have 2 different types of integers. We have unsigned integers and we have signed integers. If anyone has programmed in the C programming language, or let us say C++ or C#, are you aware about these languages, programming languages? Are you programmers? Students? Are you software engineers? Are you computer scientists? Even computer engineers? Have you seen this?
We have heard of them, but I don't think, I don't know, I didn't take C.
Okay, okay. So if you have programmed in such a programming language, you will notice that there are two different types of integers. So we have the type which is called unsigned integer, and we have the type which is signed integer, or just int. Int means signed. In Java, I think they provide only int. They don't provide unsigned int, whereas other programming languages are more rich. They distinguish between unsigned and signed integers. So here signed means in the 2's complement representation that we have seen last time. So what I'm talking about is directly related, okay, to programming. Okay, so that's also is important, not only from the design of the circuit. Of course, we need to understand this in this course, but also it has also implications. Okay, if you are programming, if you are programmers, all of you, okay, are programmers, right? So you need to understand the difference between the two. So if you have, for example, an unsigned integer, you can represent it with n bits. So the minimum here will be 0, and the maximum will be 2 to the power n minus 1. Yani, for example, if I use 1 byte will be n is equal to 8 bits. So let me write here n is equal to 8 bits. So the minimum is 0. What's the maximum if we use 8 bits? What's the maximum, students? What is this number?
2 power 8 minus 1.
Yes, which is?
255.
Excellent, excellent. 255. So therefore, the maximum will be 255. So we can go from 0 to 255 if we are using unsigned integers. Okay, we cannot represent negative. We cannot really have a number which is greater than 255 because we are using only 8 bits. Okay. In general, if you are using n bits, you can go up to 2 to the power n minus 1. Now, if you are adding, let us say, 2 unsigned integers, for example, this number here plus this number here, you might get a sum which is greater than the maximum. In this case, we say that we have a carry. So the carry will be equal to 1 if the unsigned sum is out of range. It's greater than the maximum. So if the sum is greater than the maximum, we say that we have a carry. That's the carry. That's the meaning of the carry. On the other hand, in the case of subtraction, okay, if we are doing subtraction, you might get a borrow. So if I would like to calculate a minus b, and a is smaller than b, then the difference will be negative. But there is no way to represent a negative number if you are dealing with unsigned integer because the minimum is 0. So here we get a borrow. And the meaning of the borrow, it means that the sum should be less than the minimum. Okay, that's the meaning of the borrow in the case of unsigned integers. But this is for unsigned. But what about signed integers? In the case of signed integers, we use the 2's complement representation. This is actually how this is the standard way, how computers represent signed integers. So we have 0 is in the middle. We have the minimum here is negative 2 to the power n minus 1 is the exponent. And the maximum is 2 to the power n minus 1 minus 1. So for example, if n is equal to 8 bits, let us use it for 8 bits again. So what will be the minimum if we are using 8 bits?
Negative 128.
Exactly. It will be negative 128. Thank you very much. So n minus 1 will be 7, and negative 2 to the power 7 is negative 128. And how about the maximum?
127.
Yes. So it is plus 127. So we can go from negative 128 to plus 127. And there is one representation for 0. Now that's if n is equal to 8 bits. Of course, if n is larger, we can have a wider range of values. So this is the range that we can use. This is the range of values that can be that represents if you for signed integers. Right. now what if I'm adding here two, let us say, two positive integers, and the sum is greater than the maximum? What will happen?
Will become negative.
Well, we get overflow. Yes, we get overflow. So if you get here a sum which is greater than the maximum, we say that we have positive overflow. If I'm adding two negative integers and the sum turns out to be here more negative than the smallest negative, then we say that we have negative overflow. So overflow can occur in two directions. So we use the concept of overflow when we are dealing with signed integers. So we can have positive overflow or we can have negative overflow. So positive overflow, it means that the number is greater than the maximum, and negative overflow, it means that the number is smaller than the minimum. Okay. I have examples about this, about carry versus overflow. So we have four cases. Okay, because carry can be 0 or 1, we can have no carry or carry, and overflow can be 0 or 1. Okay, it means that we have no overflow or overflow. So we have four possible combinations. So let us take a look at them. So I have four examples. The first example is that there is no carry and there is no overflow. So here I have two numbers, 15 and 8. So we can represent them in binary. We can actually add them in binary. Now notice that the final carry here is 0. So there is no carry, and also there is no overflow. I'm adding here, okay, positive 15 plus positive 8, we are getting 23. So 23 is the correct sum. So therefore it is within range. It is less than the maximum, which is 127. So therefore there is no overflow. These are 8-bit numbers. Here's an example of we get a carry, but there is no overflow. So I would like to add 15. Now let us take a look at the second number. Now this second number is shown here. Okay, that's my second number. Now we can have two possible interpretations of the second number. I can say that this number is unsigned. Now, if you are actually doing it in programming, you can define the integer to be unsigned, or you can define it to be signed. So if this was unsigned integer, it will be 248 because it cannot be negative. However, if this number is signed, then the sign bit is here. It's 1. It is negative. So the decimal value is -8. So we have now two different decimal values for the same bit pattern. For the same bits, for the same number, we can have two possible decimal values depending on our type that we choose in programming. If we choose it to be signed, it will be -8. If we choose it to be unsigned, we have 248. Okay? So we have either 248 or -8. How did we get this -8? Well, we treat the sign bit, we give it in negative weight. So this will be -128. Okay, can you read it clearly here? This is really 2. So -128 plus 64 plus 32 plus 16 plus 8, this will give me -8. If you add the weights, so the weight of the most significant bit is negative. And if you add the weights, you will get -8. That's how we obtain the -8, its decimal value. Okay, we give a negative weight to the sign bit. Now, let us just add them in binary. Now, initially, we add here 1 plus 0, you get 1, 1 plus 0, you get 1, you get 1 here. Now, here we have 1 plus 1, you get 0 and the carry. So here we have 1 plus 1, 0 and the carry. So we get the carry all the way here. So we get here carry plus 1 is equal to 0 and the final carry. So clearly, we have a final carry. That's the meaning of the carry. But there is no overflow. Overflow equal to 0. Now, why there is no overflow? Well, if you look at this number here, it is 7. If you look at it to be, it will be, if you look at this number to be unsigned, it will be 7. And if you look at it to be signed, it will also be plus 7. Yeah, it is actually plus 7 regardless whether the number actually is signed or unsigned. In both cases, it is 7. It is actually plus 7. Right. So now, if you say that, okay, if these numbers are unsigned, 15 plus 248 is not equal to 7. In fact, this number will be larger, much larger than 7. But if you look at 15 plus negative 8, it is equal to 7. So therefore, the carry here indicates that if these numbers were unsigned, then the sum is out of range. So the 7 is incorrect sum. But if these two numbers are signed, the first number is 15, the second one is negative 8. So when you add 15 plus negative 8, you get 7, which is the correct sum. So there is no overflow. Okay? That actually is the meaning, the difference between carry and overflow. So even though we have a carry, there is no overflow. We can have the opposite. Okay, we can have no carry and there is overflow. Let me show you an example. So here we have two numbers, 79 and 64. Now, in both cases, whether the number is unsigned or signed, it has exactly the same decimal value. Why? Because the numbers actually are positive. Okay, you can actually detect that, okay, from the sign bit here. So if these were signed, that will be plus 79 and plus 64. So if you add them up, you get this number. Okay, now this number can have two meanings. If this number is unsigned, it will be 143. But if this number is signed, it will be negative, and its decimal value will be negative 113. You see, how did you obtain negative 113? It's actually minus 128. So the sign bit here is minus 128. And then you have here plus 15. So negative 128 plus 15 will give me the negative 113. Right. Is this actually overflow? The answer is yes. We have overflow. Now, how did you detect that we have overflow? Well, we are adding a positive to a positive, and the sum is negative. So when you add a positive to a positive, you expect the sum to be positive. But the sum is out of range. 143 is greater than the maximum positive, which is 127. Remember that in the case of 8-bit signed integers, we go from negative 128 to plus 127. So the maximum positive is 127, and we are getting 143. So 143 was misinterpreted to be negative 113. Okay, so its sign bit, it actually is 1, and it was interpreted to be negative 113, which is a clear indication that we have overflow. So that's one way of detecting overflow. There is another way, is that we might actually get a carry. So here you can look at the last two carries. So here we have the carry is equal to 1. The final output carry is 0. Okay. Now these two carries are different. The last two carries are different. So when the last two carries are different, this is a clear indication that we have overflow. Okay. So that's also something that can be detected easily by the hardware by comparing the last two carries. Here, okay, in the previous example, the last two carries are identical. They are 1 and 1. So this means that there is no overflow. So if the last two carries are identical, here we had 0 and 0. So if the last two carries, the carry on the most significant bit and the output carry, they are identical, then there is no overflow. If they are different, we have 0, 1, or we have 1, 0, then that's an indication of overflow. I have one more example in which we have carry and we have overflow. Now here in this example, this is more interesting because the numbers here can have two different meanings. So we can interpret the first number to be 218 and the second one will be 157. If these were unsigned, then the first number will be 218 and the second one will be 157. However, if these were signed, then these are negative numbers. Okay, then their values will be negative 38 and negative 99. Now, when you add them in binary, this is what you get. You get the result is equal to 119. you get a positive result. You can see that from the most significant bit. So you are adding a negative number plus a negative number. So you are adding negative 38 plus negative 99, and you are getting a positive result. Then this is an indication of overflow. So if these numbers are signed, clearly we have overflow because we expect the result to be negative, but we are getting a positive result. Now, clearly here, by just looking at the addition in binary, you get a 1 here. That's an indication that we have a carry. That's the carry. Okay, that's my final output carry. Now, notice that the carry on the most significant bit is 0. So these last two carries are different. They are not the same. That's also another indication that you have overflow. Okay, carry is important when you are adding unsigned integers. That's when the carry is important. So when you get a carry and you are dealing with unsigned integers, it indicates that the unsigned sum is out of range. That's what it means. And the sum is greater than the maximum unsigned value that can be represented. That's the case of the carry. So the carry is important when you are dealing with unsigned integers. How about overflow? Overflow is important when you are dealing with signed integers. We use the concept of overflow. And it indicates that the signed sum is out of range. Remember the range, okay, for the signed integers. So when you get the sum is out of range, then you will get overflow. So you can easily detect overflow. For example, if you are adding two positive integers and you get the sum is negative, that's an indication of overflow. Or you are adding two negative numbers and the sum is positive, that also is an indication of overflow. There is also a simple way of detecting overflow. Look at the last two carries, Cn-1 and Cn. So we have seen that in the previous slides. Look at these last two carries. If they are identical, 0, 0 or 1, 1, then there is no overflow. If they are different, 0, 1 or 1, 0, then we have overflow. Okay. So if the two carries, so here in this example, n is equal to 8 bits. So Cn-1 is C7 and Cn is C8. So this will be the carry on the most significant bit and the final output carry. So now here we can use these two carries, okay, to detect if there is overflow. And this can be done very easily in the hardware using XOR gate. So the XOR here, the meaning of the XOR is that if the two carries are identical, 0, 0 or 1, 1, you will get 0. It means that there is no overflow. But if these two carries are different, you will get a 1 because 0 XOR 1 and 1 XOR 0 is equal to 1. That's an indication that you have overflow. Right, so how can we now do subtraction? Now we understand signed integers. If I would like to design a circuit to compute A minus B, how can I do this? Well, the idea is simple. We use the concept of the 2's complement. So to calculate A minus B, what we need to do is that we need to say minus B is the 2's complement of B. So we convert the subtraction into addition to the 2's complement. So it will be A plus the 2's complement of B. So we use the same adder in the hardware to do addition and subtraction. So to calculate A minus B, we say A plus. So we have converted the subtraction into addition to the 2's complement. So the same adder is used for both addition and subtraction. I'm going to give you an example, okay, to show you how we can convert addition into how we can convert subtraction into addition to the 2's complement. So suppose I would like to subtract these two numbers, okay? So here we have two numbers in binary, and I would like to subtract them. Now remember at the beginning of the semester when I talked about subtraction, we used the concept of the borrow. Remember this concept? I talked about it at the beginning of the semester. So for example, I would like to subtract 0 minus 1, okay? Subtract 0 minus 1, we have to borrow, okay? So we use the concept of the borrow. So basically the 0 becomes 2 minus 1, we get a 1. And this borrow is shown here on top as -1. We have to borrow it from this one. So now this becomes 0 minus 0, we get 0. So if you continue like this, okay, this is basically the difference that you get. This is the result. This is actually A minus B. Okay. Now this is using the concept of the borrow that we have studied and we have understood at the beginning of the semester. Okay, Osama, you had the question? You had the comment?
No, I was just saying about the borrow in and borrow out.
Yeah, so that we have seen that at the beginning of the semester. Yes. Now let me show you how we can do it differently. Okay, so now rather than actually calculating A minus B using the concept of the borrow, I'm going to convert it into addition to the 2's complement. So minus B will be the 2's complement of B. So we can say, okay, what is the 2's complement of B? Okay, let me clean up this, okay, my ink. Where is my mouse? Okay, so this is erase all the ink on the slide. So this is now B, right? This is now B. So in order to calculate the 2's complement, we are going to skip the 0 and the 1 until we encounter the least significant one. And then we complement all the bits that appear to the left of the least significant one. So now this is the 2's complement. Notice that this is the same 0, 1. And these bits here are just the complement. Okay? So we complement all the bits that appear to the left of the least significant one. Now we have here the 2's complement. So all what we have to do is just add. So when we add, okay, A plus the 2's complement of B, so 1 plus 0 is equal to 1, 0 plus 1 is equal to 1. We continue like this, 1 plus 1 equal to 0, and there is a carry. So again, we use the concept of the carry. Okay, there is no need to use any borrow here. Just add them, okay, like you just add two binary numbers. So 1 plus 1 plus 0, 0, and the carry. There is another carry here. You get actually 1 here. 1 plus 1 equal to 0, and there is a carry. Here you get actually 1 plus 0 plus 1, 0, and there is a final carry. Now notice that these two carries are identical. So therefore, there is no overflow. So we got the correct answer. And you can see that the results are identical. This result here and this result are identical. So therefore, we have converted A minus B into A plus the 2's complement of B. And this will give me exactly the same answer. Now, this final output carry, which is shown here, this carry here, is ignored. It's not really part of the result. We don't actually put the 1 here. This is wrong. We don't write anything because it's not really part of the result. Now, these are actually signed integers, and therefore, we simply discard the final carry. We simply discard it. And therefore, this is actually my 8-bit sum, and it gave me exactly the same result. So basically, we converted the subtraction into addition to the 2's complement. So here, we can say that A plus the 2's complement of B. Remember the 2's complement of B, we have seen that, okay, in a previous lecture, it is 2 to the power n minus B. And therefore, it is A minus B plus the 2 to the power n. And this 2 to the power n is nothing but the final output carry that we ignored. Okay, that's 2 to the power n. So if n is equal to 8 bits, then this final output carry is 2 to the power 8, which is 256, but we are actually ignoring it. Okay, so therefore we discard this 2 to the power n, and basically we get the same sum as A minus B, and the final output carry is ignored. Okay, so we got exactly the same result. Okay, if we are doing the subtraction by hand using the concept of the borrow, or we convert it into addition to the 2's complement, you obtain exactly the same result. Okay. What this means now is that I can design a circuit that does exactly this. So rather than having an extra circuit for doing subtraction, I can use the same adder for doing addition and subtraction. So let us see how. we can do this. So now I can design an adder that does addition and subtraction. So this is my n-bit adder, okay, which is used to add two n-bit numbers. So here we have A. A consists of n bits, A n minus 1 down to 0. I'm using the Verilog syntax. Notice that here I'm putting n, okay, on the input arrow, indicating that this A consists of n bits. These are n wires. And B consists of n bits. So both A and B consist of n bits. There is a carry 0. That's my input carry. And there is a carry here, Cn. That's my final output carry. Now, how do I actually control this? I would like to design a circuit that does two operations. So here I'm going to use an up. That's my input operation. And this input operation can be either 0 or it can be 1. So that's an extra input. It's an extra wire, which is used to control the circuit. So if up equal to 0, I would like to do addition. If up is equal to 1, I would like to do subtraction. So notice that here I have an extra input, which is used for addition and for subtraction. Okay. Fine. So now, if up is equal to 0, okay, what do I have to do? I would like to calculate A plus B. That's it. So here I'm using XOR. In fact, these are n XOR gates. Okay, and the reason why I'm using these n XOR gates is to obtain the ones complement of B. So when I XOR with 0, either I'm going to XOR with up equal to 0 or with up equal to 1. So up equal to 1 means subtraction. If up equal to 0, let us say up equal to 0, then every bit of B is XORed with 0. So we get B. However, if up is equal to 1, then B is XORed, every bit of B is XORed with 1. So when you XOR with 1, what do you get when you XOR with 1? If I take any bit of B and I XOR it with 1, what do I get?
The complement.
Exactly, the complement. Yes, I get B prime. So basically, I'm going to write here B prime. So the output of the XOR, so the importance of this XOR is to complement every bit of B. So this will give me B prime, which is the ones complement of B. Right. The importance of this C0 is that we can also connect this up here to C0, which means that in the case of addition, C0 is equal to 0. But in the case of subtraction, C0 is equal to 1. Now that's interesting. So in the case of addition, I have here A, here I have B. So therefore, the sum will be equal to A plus B plus 0, because carry C0 equal to 0. So you get A plus B. Now, remember that when you XOR B with 0, you get B. And when what you are adding is that you are adding A plus B plus C0, which is equal to 0. You are getting A plus B. Now that's why for addition, when the up equal to 0. However, in the case of subtraction, up is equal to 1. So when you say B XOR 1, you get the ones complement of B. That's actually is B prime. So basically, you are complementing every bit of B. So now this adder here is adding what? It's actually adding A plus B prime plus the 1, because the up is equal to 1. So it's actually A plus the ones complement of B plus 1, which is A plus the twos complement of B, which is A minus B. That's exactly what I want. I want to use the same adder to do addition and subtraction. And this is controlled by up. Up itself will tell me whether it's the operation is addition or subtraction. So you see that, okay, we don't need two circuits for that. I just need one adder for doing addition and for doing subtraction.